What I'm going to present is going to be a very quick overview of everything you're going to hear in the next 3 days. We thought it would be worthwhile to provide a sort of an annotated table of contents, if you will, for quick reference so that you have a good idea, or at least an idea, of what's in the subsequent talks that are going to extend out over a full 3 days. So this will be your introduction, and it'll be kind of a handy reference, we hope, for what will follow subsequent slides. We have a pretty tricky machine here. We'll see if we can make it work. Ah, good. Many of you have seen this diagram before. It's the uranium-plutonium nuclear fuel cycle. There's another fuel cycle which has not yet been implemented nationally or internationally, called the uranium-233 thorium fuel cycle, but this is the one that's current and will be current for a number of years. As you can see, it starts with, like, as most things do, with taking something out of the ground, mining and milling to get the uranium out of the ground. Uranium, comes in a variety of forms. Then it goes on to conversion to make UF6, which is used universally to enrich uranium. It's used in enrichment processes. Then to fabrication of nuclear fuel, which is then put into the reactor. It's pulled out of the reactor, it's stored. You'll hear more about storage later on. It's kind of a thorn in the side of the nuclear industry right now. Plutonium is recovered through a reprocessing plant, recycled back into fuel fabrication, and that's only been modestly implemented up to this point. Uranium is so cheap that we're not currently recycling uranium at all. And implicit in all of this is transportation among all of these steps, and finally there is a waste management and waste disposal function, and those are the steps that comprise the content of this course. I'll apologize in advance. I do not have slides included on waste management. We have 2 rather extensive talks which are excellent, given by Steve Cron and by John Vienna. And if I had included the slides summarizing those, I wouldn't have had time to give the rest of my talk. So sorry, John. Anyway, getting right into the mining and milling activities. You dig the uranium out of the ground. It's present in the Earth's crust in a relatively small concentration, usually a few tenths of 1%. Although there are deposits that are hydrothermally formed, which are maybe up to 60% uranium oxide. Those are rare. Uranium is not a terribly abundant element, but it's more abundant than silver and copper in the Earth's crust, but it's far less abundant, for example, than iron and aluminum. The next step is use of that conversion of that uranium to fuel in the reactors. We have a very large presentation on reactor fuels and reactors it'll the longest one in the entire course. It's you'll find it fascinating, I think. Spent fuel reprocessing is the next step. You'll hear a very good discussion of that, and it's an evolving enterprise. Processes are constantly being improved, but there are workhorses that do the bulk of it at present. There are aqueous, non-aqueous processes, then there's equipment for carrying out these processes, of which you'll hear discussed at length. And then waste forms and waste management, sometimes called the Achilles heel of the atomic energy business, because there's no really satisfactory way to manage high-level waste in the world at the present time. And then modeling and simulation, we have a discussion of modeling and simulation, which I'll just give you some details of later. Implicit in all of these operations are the fact that you have to use reagents to do the kind of separations and process steps in a nuclear fuel cycle. And you usually, these involve organic process reagents. They're subject to radiation damage by gamma, alpha, and beta radiation. And that causes some problems, and steps have to be taken to manage those degradation products. And over time, materials of construction, even like steel, they undergo damage largely from fast neutron exposure and interactions, which bounce the atoms, the iron atoms and the nickel atoms around in the lattice and give you lattice displacements, and it decreases the strength of the materials. Of course, non-proliferation is a very big deal. You see right out here in front, NNSA, which is a major DOE activity in the non-proliferation area, and you'll hear a discussion of that. Transportation, storage, and disposal is a huge area. You'll hear a very interesting talk on quantifying the risk of recycle facilities. That has not been done yet in any appreciable way for the nuclear fuel cycle. It's been done in spades for reactors. There's risk management, risk evaluation for reactors is a very highly developed process. And then environmental assessments, of course, environmental cleanup, environmental management, very important. Okay, back to mining and milling. The ores exist in deposits all around the world. We have a lot of uranium in this country. China has very little. Canada has a bunch. Australia has a lot. It can be either oxidized or reduced as it exists in the environment, and depending on which it is, that determines the nature of the process you have to use to recover it from the ores. And you'll hear discussions about that. But that's a key factor in the mining and milling of uranium ores. Milling is the removal of uranium from the ores and a semi-quantitative purification. You get a crude concentrate. In situ mining of uranium has gained a lot of prominence. You'll hear something about that. That involves pumping a solution that will dissolve uranium from an ore body. You drill a hole in the ground, you pump solution down into that hole that selectively dissolves the uranium. Then you have other holes that you've drilled nearby on the periphery that you pump the solution out that has uranium in it. And if you have the right kind of a geological environment, namely a pan of stone under the deposit, then that works. If it doesn't, the uranium goes to China. Milling is a process that you use for refining the uranium to very high purity so that you can subsequently use it to make UF6 for enrichment. I'm just giving you a quick glance at these things because you're going to get a lot of detail. The purification of the uranium can take place either by solvent extraction processes, which is sort of the workhorse, or you can take this ore concentrate and you can directly add fluorine to it, fluorine gas, which makes UF6 out of it, which is volatile, and that's being practiced at least by one company here in the United States. There are a number of processes for enrichment of uranium that have been used. The early process was gaseous diffusion, which was very energy intensive. You pumped UF6 gas through extremely fine pores in a nickel tube, and it's hard to push that stuff through. And the enriched uranium, it's uranium-235, is a little lighter as the hexafluoride than the uranium-238, so it goes through a little faster, and so you can subsequently gradually improve the concentration of UF6. Gas centrifugation is the current widely used process. We're building about 3 different centrifuge plants in this country, and there's a number of them in Europe and elsewhere. Chemical exchange is a process that the Japanese and French developed. It's basically a chemical engineering process that involves solutions of uranium. It has not been implemented industrially, although the French built a very large plant and never used it, because about the time they were going to use it, the Russians dumped a whole bunch of enriched uranium on the market, and it wasn't profitable to run the chemical exchange plants. The Japanese built a process based on ion exchange, which we at Oak Ridge about 40 years earlier had said was impossible. And they went ahead and did it, but they had 40 years of development under their belts before they could do it. And that, again, is a process that was developed on a small scale, never implemented because it wasn't competitive. The South Africans used using a German invention, aerodynamic separations. It's a sort of a form of gas centrifugation. You pump at very high velocity a UF6 hydrogen gas mixture through a tube, and it goes around a sharp bend in the tube, and the uranium-235, being lighter, makes the turn faster than the uranium-238 F6, and you can strip out the enriched part of that stream. You do this multiple times, and you get enrichment. You'll get more of this later on. Reactors, you're going to get a lot about reactors, but the current types of reactors that are in major use are water-cooled reactors, where you stick the fuel elements into a big pool of typically of natural water, like you get out of the tap, except that you have purified it pretty highly, so there's no impurities in it that can become activated by neutron capture and give you radioactivity. And there's two types of light water reactors. There's a pressurized water reactor and the boiling water reactor. The Japanese accident at Fukushima that you've been reading about was with boiling water reactors, although the accident had nothing to do with the type of reactor. It had to do more with the size of the wave in the tsunami and the fact that it washed out the power supplies for the emergency pumps. The Canadians have developed a very efficient reactor based on using D2O, heavy water, which is more neutron conservative than light water. Light water tends to absorb some neutrons. Heavy water does not. And it produces a much purer form of plutonium. The uranium-238 in any reactor fuel always captures neutrons and becomes plutonium, whether it's a breeder or whether it's a light water reactor or whatever. And so the Canadians came up with a heavy water reactor in which they could start out by using actual natural uranium. It didn't have to use enrichment. They've subsequently found it's more economical to enrich it to 1 or 2%, and so that is done. The heavy water reactor is both a curse and a blessing because it can be used with much lower enriched uranium, but it produces a much higher grade of plutonium, which can be used in weapons more efficiently than the kind of plutonium that's produced in light water reactors. That's just a little piece of gratuitous information. There also are gas-cooled reactors. The British for years operated reactors that were cooled with carbon dioxide. Currently the favored coolant is helium. We built and operated a reactor for 10 years or so out at Fort St. Vrain, Colorado, which was a gas-cooled reactor, subsequently shut down and decommissioned. The fuel was shipped off-site. But you'll see HTGRs in the future because they are useful for getting much higher temperatures than you can get in a water reactor. Water reactor is limited by the properties of water at high temperatures. You get very high pressures when you get the temperature too high. But operating on a gas cycle, you can run these HTGRs up to very high temperatures because they're made mainly out of graphite. Graphite will stand high temperatures. So you can produce temperatures that are useful for chemical processes, process heat production. And this is an up-and-coming potential use for HTGRs. It also produces a much higher temperature gas, which anybody who's familiar with the thermodynamic Carnot cycle knows that the higher the temperature you have, the more energy you can pull out of it as you drop it to a low temperature. And so it's a much more thermodynamically efficient reactor. So you'll find HTGRs looming on the horizon, and they will become I believe, quite prevalent as time wears on. And there's several countries actively pursuing them. Liquid metal cooled reactors are another form of relatively high temperature reactor. They're very useful for producing plutonium for breeding, and you'll hear a lot about that, and I won't go into any detail about that. But quite a number of them have been built and operated around the world. They are not commercial power producers at the moment. They're not producing thousands of megawatts hooked into grids, but maybe in 50 years you'll see quite a few more. It'll be a while. They can also be cooled with lead or low melting eutectics of sodium and potassium, and both have been used. And I won't say anything more about that. Alan Croft will talk about those in length. And then there's the molten salt reactor, which is made of fluoride salt, zirconium fluoride, lithium fluoride, uranium fluoride. And these were built and small pilot scale operated at the Oak Ridge National Laboratory. There's still a good deal of interest in them, some in India and in some other in other countries, China. But they'll be a while, I think, in being commercialized also. They have advantages and disadvantages. That you can process the fuel on stream by taking a side stream of the molten salt off, do processing out, put it back in the reactor. You don't have to take fuel out of the reactor, chop it up, and process it. There are a number of kinds of reactor fuels. The water-cooled reactors are primarily pellets, half an inch in diameter, half an inch high of uranium, 4 to 5% enriched uranium in the isotope 235 as the dioxide. And they're slid down into tubes of zircaloy metal, which is a zirconium tin alloy, and sometimes a few other things added in to increase the integrity of the fuel cladding. And these things can be anywhere from 6 feet to 12 or 13 feet tall, these individual tubes, which are assembled in bundles and stuck into these power reactors. Gas-cooled reactors are, again, UO2 pellets, and they can be in the zircaloy or steel, and have been. The uranium carbides, such as are used in high-temperature gas-cooled reactors that I mentioned, or in carbide fuels, are also potentially of use in these liquid metal-cooled reactors. And their advantage is they will stand higher temperatures than the oxide without undergoing serious malformation due to radiation damage. And the graphite fuel elements can either be, the Germans have developed little graphite balls, which it's sort of like a rice pudding. You have a lot of little particles, uranium oxide or uranium carbide, in a graphite matrix. Then you put a graphite layer around the outside. Then these balls are all thrown into a big pot, and that's your reactor. And then they shove a bunch of control rods down into these balls, which they're kind of greasy, so they move being graphite, so they move aside, and you can slide the control rods up and down and control the reactor. The alternative fuel form is prismatic graphite blocks. They're about 14 inches across, hexagonal, and about that high, and that's what was used in the Fort St. Vrain reactor for about 10 years. In my judgment, the prismatic fuel form is a more likely one to survive because the graphite balls require processing by taking the balls out one at a time, interrogating them with a counter that counts neutrons and gamma rays, and depending on the amount of fuel that's been burned up in the balls, they either are processed or put back into the reactor. And of course, you got a bunch of balls in a big cylinder, a funnel at the bottom, and you don't know exactly where the balls came from as they come dripping out the bottom. So I think the prismatic blocks are more likely. The liquid metal reactors, the sodium potassium eutectic mix that melts at a fairly low temperature, cooled ones, you have UO2 pellets, or there's a lot of fuel development work going on to develop much better fuel materials that will go to much higher burnups, as we say. The time it's spent in a reactor is called the burnup. And it will maybe go to twice some of these uranium, zirconium, plutonium alloys, maybe twice the burnup of the oxides, which I think is a real plus. But there's a lot of development work going on in DOE and NE right now. Carbide fuels are under development. They're very actively being developed by India, and they have them in reactors over there. And nitrides are also under development. Nitrides have an inherent disadvantage in that nitrogen captures neutrons and becomes carbon-14, which is radioactive and is a potential problem when you get to reprocessing the fuel. Molten salt reactors are, as I mentioned earlier, are a molten mixture of alkali fluorides and uranium and zirconium that are, and the fuel, the molten fuel in the reactor, it's sort of a, Alan Weinberg used to describe it as a pipe, a pump, and a pot. So what you do is you pump this molten salt around in a circle, and it comes to a bulge in the pipe. That's the reactor, because you get enough to get a critical mass. And then you can take a side stream off for reprocessing. There are a lot of advantages to a continuous process, but there are a number of disadvantages as well, as you'll hear. Spent fuel reprocessing is a very widely practiced thing internationally. The current process is called the PREX process, based on solvent extraction. You dissolve your fuel up in nitric acid. You mix that up with an organic phase, which is triene-butyl phosphate dissolved in kerosene or normal dodecane usually. And the uranium and plutonium pop up into the organic phase because they're more soluble there than they are in the aqueous phase, and there are chemical reactions that bind them in the organic phase. And then you separate the two phases and you have the uranium purified. You'll hear a lot about that, but there's a number of steps required there to get the kind of purity you need. You need something like 10 to the 9th, which, you know, it's not like falling off a log to get that kind of purity in the plutonium and uranium products. Earlier there were other processes that were practiced. The most best known in this country is the redox process. It was practiced at Hanford for many years. And then there was a number of miscellaneous processes that other countries had developed based on esters and amines. One of the earliest separations reagents was diethyl ether, but they had to stop using that because they kept putting people to sleep. That's a joke, folks. What really was the problem was that it was very volatile, and it's highly flammable, although it was very efficient for extracting uranyl nitrate. There are non-aqueous processes that have many advantages over aqueous processes, a number of disadvantages. So things are always trade-offs in this business. Pyro processes, which you'll hear about, that involve very high temperatures and a number of operations involving molten salt systems. I won't go into detail on those. You can also directly volatilize things like uranium and plutonium by fluorination or chlorination, and most other elements in the periodic table do not volatilize, although some do, and they cause problems in the separations. But not many things form extremely volatile halides, and so you can use that to selectively separate uranium in particular. Then what I call Dupic type processes, which are currently under active development by DOE, and you'll hear more about these, a lot more about these later on. These are essentially low decontamination processes. Instead of getting this 10 to the 9th, maybe you get 10 squared, maybe you get 100 DF. It means a lot of radioactivity left in the fuel. So all these separations are entirely carried out remotely, and the subsequent fuel fabrications using these materials are carried out remotely in hot cells. Nonetheless, they have a number of advantages, and I think you'll hear some about that. So kind of keep your eye on these low decontamination processes, because there's a lot of development going on in DOE-NE as we speak. Of course, carrying out all these kinds of separations I've been talking about, whether it's the mining and milling operations, refining operations, or whatever, you have to have equipment. And the equipment comes in several types, usually for very large volume activities, like out in the mining and milling of uranium ores. You use mixer settlers, which are big, large trays where you have the organic and aqueous phases mixed with some kind of a stirring device, and because they're two separate phases, the top phase flows out over a weir, and it's separated that way. And so you get a separation of the phases. There are also big columns that can be 15 feet tall, and the diameter of them is controlled, limited by the enrichment of the uranium that you're processing. If it's high enriched uranium, you want a relatively small, like maybe 6 inches in diameter column or less. If it's uranium ore that you're processing, then you can have a big column if you want to do it that way. And the columns can be either of two principal types. One's called a pulsed column, in which the aqueous and organic phases, maybe you fill the column with the aqueous phase, the uranium dissolved in nitric acid, and you pump the organic phase in the bottom, being lighter, it floats, and it goes up, and it meets, as it comes up this column, it meets a plate that impedes its flow, and this plate has a bunch of holes punched in it. And as the organic phase comes up and gathers on the bottom of this plate, it's squeezed out through these holes, which gives you little tiny drops, which gives you a lot of surface area, which allows for a very efficient extraction because you have a lot of surface area that you're extracting from. So that's the principle of a pulse column. A packed column is the same thing, except instead of a bunch of plates, you just fill the column full of a ceramic, little pieces of ceramic, and as the organic phase winds its way up through the ceramic, it gets broken up into droplets, makes better contact with the aqueous phase, you get better extraction efficiency. And you'll hear about all this in much more detail. The current movement is toward what's called centrifugal contactors. These are cream separators in principle. You've heard of, those of you who are as old as me know about the old Duval cream separators. Nobody here does. And basically what you do is you take uranium hexafluoride, which is a gas, you spin it very, very fast in a centrifuge. The uranium hexafluoride is centrifugally spun to the outside of this, the inside of this outside tube, and it makes a very thin layer on the wall. And the UF6 is a little heavier than the UF5. Uranium-235 hexafluoride is lighter than uranium-238 hexafluoride, so it's on the inner layer, and the uranium-235 is on the inner layer, and the uranium-238 is on the outer layer. And you take a fine scoop, and you scoop off that inside layer, and you run it to another centrifuge, and you do it again, and you do this about 500 times, and you get pretty highly enriched uranium. So that's the principle of centrifugal contactors for enrichment. For solvent, for reprocessing, the same principle exactly, except you have an aqueous and organic phase. Again, the aqueous phase is more dense than the organic phase, and it spins to the outside. The organic phase is on the inside, so you take off the outside layer and move it to another centrifuge, and you take the inside layer and move it in the opposite direction to another centrifuge. And by doing this, as we say, countercurrently, as you'll hear about this, and you'll actually see diagrams of countercurrent equipment later on, by doing this you get a separation of the uranium from the fission products, which stay in the aqueous phase. Well, solvent extraction consists basically of three operations. And as I said, solvent extraction with the PREX process is what's used universally to reprocess irradiated fuel from these light water reactors. And the extraction step can either be done in columns, as I've mentioned, or in centrifugal contactors. No extraction is ever complete. It's a law of nature that no separation of anything is ever complete from anything. So you do wind up getting some impurities in the purified organic phase that's supposed to contain just the uranium and plutonium. You get little emulsions, you get little droplets that contain the aqueous phase, which contains the fission products. They wind up in the organic phase, and so you have to scrub those out. So you take a little nitric acid solution and you dribble it down through the organic phase, and it takes out these tiny dispersed droplets or a small amount of extracted material, because some of the fission products are slightly extractable. And so that's the scrubbing step. And then when you're all done with that, then you have the uranium and plutonium pure in the organic phase. You got to get it out, and that's called stripping. And you do that with a dilute nitric acid solution. It turns out that favors movement back into the aqueous phase, so you strip it. And again, you'll see this. You'll see diagrams of the equipment that's used. You'll hear a discussion of countercurrent extraction. But this just gives you an outline of what the steps are. There are some requirements on the solvent extraction equipment. It has to be capable of handling a fairly high throughput. If you're going to have a large plant, you might have a 1,000 metric ton a year plant, a 1,500 metric ton a year plant, big plants. And so the equipment has to have high capacity. Pulse columns do have high capacity. Centrifugal contactors have even higher capacity because they're very fast. The equipment has to be operable in a highly radioactive environment, which means you can't do it hands-on. You got to do it remotely. And some of the equipment is subject to radiation damage. If you have sensors in it, you have electrical leads, you have sensors. Maybe you're measuring the pH. You might be measuring the conductivity, and all of the wires and all the things that you have in the way of equipment are subject to radiation damage. So the equipment has to be quite radiation resistant, and all equipment fails from time to time, and it has to be able to be remotely maintained. Some equipment fails more than others. Centrifugal contactors, being a very high-speed device, are more subject, for example, to failure than pulse columns are, although they're certainly practical devices. And it's sort of inherent in any process that no matter how hard you try, you don't get them really pure. You don't get your materials pure. And we've developed a very sophisticated term for the kind of impurity that forms. It's called crud. So crud accumulates in some of these columns, and you have to have ways of removing the crud. And then the solvent has to be, the organic solvent has to be recycled because it has to be reused over and over, and it does suffer radiation damage. And you take some of the crud of radiation damage out of it by processing the solvent and recycling it. Well, there's other things in the world, processes that can be used besides solvent extraction. And certainly the very early stages of the whole nuclear enterprise, precipitation and crystallization were processes that were very widely used and are used today in all parts of the fuel cycle. For example, the fabrication of fuel, you'll precipitate some of this purified uranium as for example, ammonium uranyl tricarbonate, which then is decomposed to form a very pure uranium oxide. So precipitation of various products is prevalent and widely used. And in fact, the first tiny amount of plutonium that Glenn Seaborg and co-workers separated was done by precipitation using bismuth phosphate. And still today, in some uranium and plutonium processes, purify these materials by selective peroxide precipitation. Turns out that hydrogen peroxide, when added under the right conditions of acidity and concentration, will precipitate quite selectively plutonium and uranium. It's not highly quantitative. There are some losses and you have to recycle streams, but nonetheless you get a very pure product. So precipitation is a widely used process. Some precipitates are mean. For example, if you precipitate uranium as iron as a hydroxide, it's gelatinous. It's not crystalline. It's not a powder. It's sort of like Vaseline, and you want to avoid those kinds of precipitates whenever possible. And precipitation is used fairly widely in the nuclear industry. Ferric hydroxide, properly prepared, is a useful scavenger for almost anything. If you have impurities in your process water stream that's leaving a reprocessing plant or a purification plant, and you can't just dump that impure processed water out into the world, so you scavenge out all the impurities, or most of them, by precipitating either with ferric hydroxide or with phosphates. There are some phosphates which absorb impurities sort of indiscriminately, and so they're very good for taking out impurities. Crystallization is a process which is pretty neat because when a crystal forms of a material, it just wants to be that material. It makes a nice crystalline lattice, and some impurity comes along, and basically the crystal says, you don't belong in this lattice, you're either too big, you're too small, you got the wrong ionic charge, and I'm not going to let you in. And so the crystalline products are pure. And so by crystallization and recrystallization, you can make a very pure crystalline product. A lot of the actinides give you a little bit of grief here because the chemistry of many of the actinides is very similar. They are all in one family, one chemical family, so there's a large chemical similarity among them. And so they behave like a single element in some cases, and so it's hard to get a pure product. But Gordon Jarvinen will tell you all about this and in a lot more detail than I'm giving you here right now. Now, modeling and simulation is receiving a lot of attention by the Department of Energy, and for good reason. It's possible by modeling and simulation to do a great many beneficial things. For one thing, if you're in the experimental world, you can avoid doing many millions of dollars worth of experiments by modeling the process that you're interested in, and essentially using a computer to run tests on the process. You have to know, of course, some inputs. You have to know some chemical properties. You have to know what the material is and how it behaves chemically. But this information is either known or fairly readily obtained experimentally. And then once you get a little background of accumulation knowledge, then you can use this in a whole variety of ways. This chemistry applies in a variety of ways, so you can simulate a great many of these processes that I've been discussing very quickly here using computer models. And you can simulate, for example, the solvent extraction processes. You can simulate that, and you can say, what if I change the flow rates of the aqueous phase and the organic phase? What will this do? And how will it affect the purity of the product? How will it upset the column operation? And that can be simulated very nicely. So any aspect of the fuel cycle can be modeled with a computer, and the processes can be simulated. And then you can also use modeling to develop better reagents, and there's a fair bit of work going on that way. Somebody comes along and says, I've discovered a solvent extraction material that really is pretty darn good. And somebody else says, yeah, but what might make it better? Well, what might make it better, for example, if it's an organic extraction, is maybe you stick a little methyl group on here, or you stick a little hydroxyl group on here. You can do this by modeling, and you can determine what, up to a point, what the effects of these things will be. You need the basic input. You need the parameters to start with. You can't just say, I've got the universe, and I'm going to pluck something out of it and develop a better solvent extraction reagent. You have to have a point to start. But when you got that point, then modeling can save you a tremendous amount of experimental work and design. Well, there's several different types of radiation that you run into in the nuclear fuel cycle. Photons, of course, are X-rays, gamma rays, ultraviolet and infrared radiation. All of these play a role one way or another in the fuel cycle. There's electrons, there's alpha particles, and I don't have neutrons up there, do I? I wonder if I have them. There are neutrons. And typically the neutrons that are damaging are the ones that are fast. When uranium fissions, it produces very energetic neutrons. They're up in the hundreds of millions of electron volts. And when they strike a material, they may knock a dozen atoms out of place in a crystal, in a metal. And then those atoms either relocate back into the proper place in the lattice, or they don't. Or maybe in graphite, they will they will displace graphite atoms. One of the problems in the early graphite reactors was that there was something called the Wigner effect. It turned out that the graphite over time would grow and it would distort, and nobody quite knew why. And then finally Eugene Wigner said, well, it's the fast neutrons. They're knocking heck out of the graphite atoms, or the carbon atoms in this graphite, and when they fall back, they don't fall back into the right spot in the lattice. So fast neutrons are a very important thing. Of course, one of the things that people really worry about is what are the biological effects of radiation, and there are plenty. But like most things, it cuts both ways. There's the gamma knives that cut out cancers, and there's X-rays that similarly are used in many medical treatments, as well as in looking at the insides of people and things. So there are both beneficial and harmful effects of radiation. In the processing area, the nuclear fuel cycle area, there's damage to all of the materials that are used. Where the radiation field is very high, where maybe you have a lot of fission products, then the damage is also is correspondingly high. Where the radiation is very low, you might go for years without any noticeable effect. And then I mentioned the effects on various kinds of equipment and materials that are used in building reprocessing plants and in putting into proper sensing agents. There's the ever-present worry about proliferation. The major concern with proliferation, of course, in this country is not that somebody's going to steal a critical mass of bombs worth of plutonium. The major concern is that Iran is going to produce bomb-grade uranium in their gas centrifuge plants that they're building. So but nonetheless, there is a concern. We'll be storing 2,200 metric tons of spent fuel every year from our current 104 processing reactors on site, either in pools or on pads at the reactors. And there is some concern that this is a proliferation risk. Not much of one, because these things are huge. These containers that the fuel elements are in, you're not going to drive up with a pickup truck and carry one away. But in the movement of the uranium around in the plant, and especially in reprocessing plants where the uranium and plutonium are no longer in the fuel cladding, they're in solutions, or they're as oxides, powders. The possibility exists to steal this stuff and make a bomb, or try to make a bomb, or at least threaten. Say, I got the material to make a bomb. I'll need $10 million to go away. So, and there's in proliferation, we have the countries that know about that are developing weapons, and then we have those that we don't know about that may or may not be developing weapons. And that's one of the functions of the NNSA, to keep an eye on that stuff. And then we have the issue of detecting potential clandestine fuel cycle activities in rogue nations. So proliferation is an ever-present issue in the nuclear fuel cycle, and it varies in its degree of importance depending on the country and on the process that's under development. And you'll hear quite a bit about proliferation from a real expert in the business. Transportation and storage, that's critical to the whole nuclear enterprise. Doesn't get a lot of discussion, but you got to move things from place to place or nothing works. This pretty well lists the things that I've discussed previously. Right now we're storing, as I said, the fuel from these 104 reactors right where it's being irradiated, and in reactors we're storing it in the spent pool storage pools, or in concrete vaults on big concrete cylinders on big pads out by the reactors. The utilities are not crazy about this, I might add. They're very anxious to get these spent fuel or used fuel materials off of their sites as was promised to them, and has never taken place for various political and practical reasons. And then there's permanent disposal, which was meant to solve that problem, where we have the Blue Ribbon Commission under active deliberations now, but it looks like their conclusion will be, for the time being, we're going to store the stuff. Although they've only come out with just hints of what they're going to say, they have hinted that. And the other option is the much longer term option, maybe in a 20 to 50 year, probably closer to 50 year time frame, where instead of just taking this spent fuel and storing it, you process it, you recover the uranium and plutonium, and then you wind up with a bunch of fission products and a bunch of other actinide elements, americium, curium, neptunium, for example, and you stick those in a one of these fast reactors that I talked about that's cooled with molten metals, and they are called actinide burners. And one of the problems with storing spent reactor fuel or reprocessed waste from fuel is that it has a lot of actinide elements, americium, curium, neptunium. These are very long-lived. By and large, they're alpha emitters. They generate a lot of heat. This causes a real problem in storing it, because the geologic repositories, a lot of modeling has been done on this, they get hot. That means you can't store these things real close together, so you get a bigger repository. So the thing to do is to burn them. Basically what you do is you convert them to fission products. So you have fission products instead of actinides. The fission products decay with a shorter half-life. They're much more tractable. And then you stick those in a geologic repository. You'll hear a discussion of methodology for discussing risks. And certainly there are risks in the fuel cycle. These are reactor risks, but there are potential risks in reprocessing as well. And then everybody worries about what you're dumping into the environment, and they should. And you have to have, when you run these processes, nuclear fuel cycle processes, you have to have an environmental assessment, which gives you various options for various methods of handling the materials that are being produced, and you present these options in what's called an environmental assessment, and then the people decide what's the best way to handle the material, the safest way over the long term. Those are called scenarios. And the assessments will cover these kinds of considerations. There are also economic considerations. And Mike Greenberg didn't give a talk. He was scratched. I'm not going to take any questions, because you're going to hear much more detail, much more detail. It's got 3 days of this, of each of these topics. But this is your quick overview. It gives you a reference sheet to look at when you're interested in something. It'll tell you where to go in your book from these real experts in each of these steps, and they probably will tell you that they are available for discussion as well offline sometime in the future. Thank you.